Okay, so I recalled on the left blackboard the conclusion of last lecture. So we had a general system of pseudo-differential equations with two types of terms. There was one type of term which was corresponding to a multiplier of degree alpha, which was skew symmetric, and another one of degree beta, which was symmetric, but only partially symmetric. I mean, which was non-negative, but maybe not positive definite. So after, so we applied the Fourier transform, and for each frequency, it turns out that you can find rescaling that reduces the problem to this one, which is just a system of ordinary differential equations with constant coefficients. So the goal was to get estimates of the norm of y as precise as possible estimate. So the first one was just something that we could call energy estimate. Okay, you take the scalar product with y, and you end up with this by using two properties. The first property is that A is skew symmetric, so you don't see this term. And the second one is that you have some inequality from below for B. Okay, so if B is a positive definite, then it's good because then it's equivalent to Y, and this gives time exponential decay. But this is not the situation I am interested in. I am interested in the situation where there is some degeneracy, so that you cannot bound this from below by a constant by Y square. So the next step is well, to get more information, and it's not just by playing with the equation, by looking by this combination. Then maybe I forgot to tell this, but you have, in order that the computation is exact, you have to take the real part. Okay. So you get this identity. So you generate a new positive term, but you have new terms. So in the new terms, there were three new terms actually. There was one multiplied by S, and over two terms that were good in the sense that it was possible to absorb them by just by playing with Cauchy-Schwarz inequality or some relative inequalities. It was possible to absorb them by either this or this one. Okay, once you multiply this by some suitable coefficient. So the problem was this new term that you don't know how to handle, because here, even if you use Young inequality, you will get either By, so By is good, but you have this one, and this one you don't know how to handle, because it's not of this type. Okay, so on the toy model, we did the same, but we did not have this problem because for the toy model, it turns out that the square of A is the identity. Okay, so this term is exactly of this type. In general, the situation is not, it's not necessarily the case. So you have to go further in the computations. So the idea would be to generate a relation where this quantity appears with a square. So it would be step 2. For step 2, you will consider the combination BAY and BA square Y, and so on. But every time you generate new terms. So as step K, if you look at this combination, so you have a positive term that is good because it will allow you to absorb the bad term from the previous step, but you generate a new one, which is bad because you have a K plus 1. So the question is whether you have to do this an infinite number of times or not. The answer is we are saved by Cayley-Hamilton theorem. It's just a linear algebra, actually. Okay, we said that you may express. If you have to remember that all these objects are matrices of dimension n. So you are sure that you can express a to the n in terms of lower powers. So this term, for example, you are safe because typically you can, so AN is a linear combination of identity A and A minus 1. Okay, which means that when you arrive at step n minus 1, so the new bad terms will have a to the n, but the a to the n will be expressed in the terms of lower powers that have been already treated. Okay, so this is in principle. So in fact, the process will end after n steps. The only difficulty is to find some combination that indeed allow you to kill all the right-hand sides. So it has been done by Bochard and Zouazoua. And in fact, let's call it Bochard and Zouazoua functional. So it's strongly inspired by Kalman theory on differential equations. He said that one can find parameters epsilon 1 to epsilon n minus 1, small and non-negative. Not only small, but as small as you want, in fact, okay? Such that the following functional, let's call it L square equals y square plus the sum of, okay, all these terms, no, all these ones. Okay, so sum from k equal 1 to n minus 1 of epsilon k real part of b a k minus 1 y b a k y. Okay, so such that this is equivalent to y square. So, for example, such that this is equivalent to y square. Okay, you can choose a factor as close as 1 as you want. Yeah. No. Somehow we completely forgot the dimension of the space, the variable. This is just, we reduce everything to I mean, the dimension of the space is hidden in the fact that at the beginning, A and B were depending on some parameter omega, which belongs to the unit sphere, and S is the frequency. But at this level, in fact, you can completely forget that there is dependency for these computations. In the end, you will have to remember, for example, here, you will have to remember that you may ensure that these parameters are uniform with respect to omega, just because the sphere is compact. Okay, and so n is the size of the system, actually. So you are right, negative, and I can precise that they are independent of omega. Well, I mean, if you have in mind the initial problem, it's important to precise this. And in that case, in fact, this B and A depend on omega, okay? So you have this functional, which is equivalent to y square, and such that 1/2, or maybe I could remove the 1/2 of L square plus, sorry, I forgot something very important. So I would put it in orange. Of course, there should be some dependency with respect to S. And the dependency is the same as for the toy system, you have put the mean between S and S minus 1. Sorry for that. Okay, and then it's equivalent to y square. And such that you have this inequality, you have the minimum between 1 and S square divided by 2. Okay, and then you have a sum which is which corresponds to this one actually. Okay, so you have okay. Let me put by square. So you understand why I put 1/2 because it cannot be greater than 1 because you start with 1 here, but you lost something because you had to kill all the terms. And then there is all the over terms. So from k equal 1 to n minus 1, and of b k y square. So all this is smaller than 0. Okay, so now the question is what can be said? Sorry, again, I forgot the parameters. Epsilon k. Okay, so now the question is what can be done with this? If having in mind the toy model, you want to get some exponential decay from this inequality, but for that you have to be able to bound this term by some constant by L square. So is it possible? So there's something that you can always do is to define some number, non-negative real number, saying that this is the minimum, infimum, actually it's even the minimum for so how I can say that for L. Okay, so you see that this L depends on Y. Okay, so there is so this L is a L of Y, if you want. Defines from Y. So you define the minimum for Ly equal 1. In fact, it's a kind of sphere. It's well, for y equal 1 will be exactly the sphere, and we take the minimum of all these terms. So okay, for b of which is inside the parenthèse, by square plus sum k equal 1 n minus 1 epsilon k b a k y square. Okay, so here you have a compact set. Okay, so this is indeed a minimum. This is non-negative. And okay, so now once you define this quantity, so clearly you have this relation plus mean of 1 and s square divided by 2 n omega L square, and you have exponential decay. Okay, which implies that L square is smaller than L square 0 times exponential of minus 1/2, the minimum of 1 and S square, times n omega t. Okay, so the question now, if it may happen that n omega is 0. Okay, so in which case not very interesting. So this inequality becomes interesting if you can ensure that n omega is positive. So when is it true? N omega is positive means that somehow by doing all this combination, you recover the norm of y. Okay, you have just partial information everywhere, but you have enough to get the full information for y. So you have for this you have let's call it a linear algebra lemma. That I give you as an exercise. So the following properties are equivalent. Okay, so the first one, the first one is that this quantity n. In fact, I mean this linear algebra is just a linear algebra which says something on a couple of matrices A and B. Okay, there is no really need of dependency with respect to n omega to omega, but as I already defined this definition, let us keep this at this. So the first is the fact that n omega is positive. The second is the fact that the spectrum of A plus B is included in the set of complex number with positive real part. The third one is the so-called Shizuta, SK condition, which is something which is well known by people that work on hyperbolic systems. So SK means Shizuta Kawashima. I don't know, Kawashima discovered this condition in his thesis. Probably Shizuta was an advisor, I don't know. Kawashima condition, which said that exactly that, assume that if you have some element in the kernel of B, and you assume in addition that V is a eigenvector for A. So if you have the two conditions together, then necessarily V equals 0. Okay, which means that somehow the eigenvectors of A have to be damped by B, which explains why in the end you have some decay. And the last condition, the one which was in fact pointed out by Bochard and Zoisois in their paper, is the link, the relation with the control theory. So it is a so-called Kalman rank condition. So the so-called Kalman rank condition is a usual one. It said that if you look at this huge matrix, okay, you start with B, then BA, and so on until BA K minus 1. Then this rank is equal to N. Maybe I should, sorry, I did something a bit stupid. Sorry, well, what I said is true, of course, but no, condition 1 is true, but it's not what I want. It's better to say that, that one can find some combination of that, which is, how can I say that? No, it's, okay, no, it's correct, but I have to do something. It has to be positive for some choice of epsilon 1, epsilon n minus 1, not for all. You just need to find one for which it's okay. Okay, I am not going to prove this property. It's not very difficult. I mean, it's basic. It's mostly linear algebra, except maybe the second one. The second one somehow it's a consequence of the computation that have been done before. Okay, so now the question is, so this is true for any omega, but now if we want in the end to get, if we want to go back to the initial problem, which was to get some decay properties, some estimate on some system of pseudo-differential equations, we need to have this condition for all omega. And again, if it is true for all omega, so if one of the four conditions are true for all omega, then since omega belongs to the sphere, by compactness, you will have some parameter which is still, so the infimum of all this will be strictly positive. Okay, so let me call n étoile equal the minimum of all n omega. So what I can say is that from the inequality that I proved before, I can say that for all we have this property L square, which actually also depends on omega, is smaller than, well, the same. L square 0 omega was the same exponential factor, minus n star divided by 2, the minimum of 1 and S square t. Okay, so now if you go back to the initial problem, so remember, sorry? Yeah. Yes, sorry, no, yeah, sure. It's not case, n minus 1. Okay, so here, in fact, you have a huge matrix with, how you call this, n columns and n square rows. Okay, so you can do, very informative to do the computation with just for Euler system. Okay, you will see that for Euler system, you don't have to compute everything. You may stop here, and by looking just at the first two terms, you already have rank n. Okay, so if I go back to the original equation, so which was this one, what do we get? What do we get? So, okay. I can put even, well, no, let me do this. So remember that we had a change of variable. So the hat t psi was corresponding to y tau s omega with, so the relation was tau equals t what did I do? Yeah, t rho to the beta divided by kappa, and S was R alpha minus beta kappa. And remember that psi was written like R omega. Okay, so now if I use this inequality and make the change of variable, then you will end up with the following. And also you use the fact that L is equivalent to the L square equivalent to the norm of y square. So what you get is this inequality. well, the L is defined from Y. Yeah. Yeah. So yes, defined for all Y. It's defined from Y. Maybe my notation is not good. It's defined in this way. So it depends on Y. Yeah, you're right. I mean, this is a L. How can you say that? No, okay. So my notation is not good. The dependency on Y is corresponds to the dependency on omega. So it's difficult to find good notations with that. You can keep all the time. Okay, so I go back to the original variable, and then what I get, I remove the square, and if, for example, you manage that in the equivalence here, you have a constant 4, then after you can manage to have this. C hat 0 psi. And what is interesting is that you get inside the exponential term. So inside the exponential term, you will have, well, some constant. So you have to divide by something, maybe by 8. I mean, it's due to the fact that you have several times to go between L and Y and so on. So you do something, but not too much. And which is important is that you have the n star. And which is really interesting is that you have the minimum that you get is psi to the beta divided by kappa, and kappa psi to the 2 alpha minus beta and t. Okay, and now if you still have the table that I draw the first day, maybe it was only for alpha equal 1 that I did it, then it will correspond to the two regimes where the two regimes, you keep the worst exponent, okay? So it's not still not completely satisfactory because this is, what is not completely satisfactory is that you have the same behavior for all part of Z, okay? But still you can, with this inequality, you can distinguish between the two regimes. So now what I can say, if I concentrate on a particular case, we're interested in, so it was alpha equal 1 and beta is either 0 and 2. So I don't know how you can explain this, but in fact you will get exactly the same exponents if you put either just damping or a Laplace operator. Maybe the first time I saw that, I thought it was a bit strange, but at this level, you cannot make the distinction, okay? So in that case, what you get is just the minimum between, I remove kappa, okay, for simplicity. Kappa equal 1. And so what you get is a minimum between 1 and psi square. Okay, so what does it mean? It means that you can proposition, if you like. So assume that SK, the Shizuta-Kawashima condition is satisfied. For every point, so for every omega. Then in this case, the n star is positive, and then you can repeat exactly, once you know that it's positive, the exponential factor you get is exactly the same as for the term model, and then you just have to do the same computation. You don't have to do them again. I did them. Nothing will change, and then you have for all S. Well, if you just look at estimates, you have exactly the same estimates at what I did before. So you have this one. S to 1 plus, so if you do time integration, then you have to make the distinction between the two regimes. So for low frequencies, you gain two derivatives, but gaining two derivatives somehow it's not good. And for high frequency, you gain nothing. And then you have the right-hand side. So it's bounded by some constant. The constant is not 1 if you keep the usual norms, just because, well, in order to have constant 1, I would need to define a norm which related to the function L, actually. Okay? Otherwise, I lose 1. But well, I think that this degree of generality is not very useful to track the constant. And you can even afford to have a right-hand side. The F is in the case where I put a F here. Okay? If I put a F, then just by dual-made formula, you get in the same stroke this inequality. Okay, so I got something for the linear equation at a very high level of generality. You can prove exactly the same kind of inequality for any values of alpha and beta, provided that alpha is different from beta. Otherwise, another story, then you have to do, probably still works, but well, there will be only one coefficient here, the one index of regularity for sure. So is it good or not? There is something which is a bit not satisfactory, a bit puzzling, is that, as I said, you get exactly the same inequality if you put a damping term of a diffusive term like Laplace operator. A bit strange. So in order to get something better, is it tempting to see if we can define something like for the toy system, what I call a damped mode? So can it be done at this degree of generality? The answer is yes. If you make some more hypotheses, I will not. Okay, I will give an example of hypotheses that work. Certainly, it's not the general ones, the most general ones that you can do, but at least. So let's call it the damped mode, or damped or diffusive because it depends. Damped is the right terminology if beta equal 1. Otherwise, it would be better to call it diffusive. So I will make more assumptions. My assumption is that I have a block structure. It would be easier to do it in that way. Okay, what I mean that I can split Z into two parts. Okay, one part with N1 component and another one with N2 component. And that I can write my operators, my matrices operator A and B by block with 4 blocks. And I assume that, which is important, is that I assume that B has only one block. So is it really restrictive? It's not that restrictive because if you think, I didn't assume that B is symmetric, but if you assume that B is symmetric, then you can use basis of orthogonal basis to reduce to this case, where maybe the decomposition is going to depend on omega, but it's not very restrictive, in fact, what I said. And for sure, it's satisfied by the Euler or the compressible Navier-Stokes equations. Okay, so in that case, my system reads dt z1 plus r1. I will remove the d, okay? But remember, this is not matrices, it's operators here. So differential operators. Maybe I should better put one, sorry, on the top. Okay, so this is the first equation. You have no diffusive or damped part. And the second one reads as follows. There's 1 to 1, Z1 plus 1 to 2, Z2 plus C Z2 equals 0. Okay, and just by arguing as for the toy system, this part was the damped mode, okay? Well, except that I had no A22. But apart from that, this part was okay. So let's try to do the same. Or equivalently, let me define the candidate for damped mode to be dtz2. Okay, so up to the sign, it corresponds to what I did for the toy model. Okay, and let me look at the equation which is satisfied by W. Okay, so well, it's very easy because actually what the equation satisfied by W. So I take the time derivative of this one to get an equation for W. Okay, so dtW. So this term will give exactly the C dtW. And then I have two terms in the right-hand side. dtz1 and minus A22 dtz2. So this one is again W. And what is this one? So this one has two parts, which are given by the first equation, which are so E21 A11 Z1 plus E21 E12 Z2. And I said the last term is just W. Okay, so what can be done now? So the idea is that for the toy model I saw, what I did, I just look, sorry, there is no DDT here. Okay, so now if I perform energy estimates, I localize my equation, what I did before, by the little by operator. So can we say that the right-hand side maybe is negligible or has been treated before? The answer is yes. So there are two different cases. Assume, well, just to fix the ideas, assume that I am in the damping case. Assume, so remember that alpha equals 1, and assume that beta equals 0. So what happens? So in that case here, you have something which is of order 2, okay, because you have twice an operator of order 1. Here is also of order 2. And here is of order 1. So this means that if you are in the low frequency regime, order 1 operator is like multiplying by the size of the frequency. So if the frequency is very small, it's good, something which is really small compared to this one, because in that case, C is of order 0. Okay, so in the low frequency regime, this term is negligible compared to this one. Okay, so it's exactly what I did for the toy system, except that I don't want to do again all the computations. And these two terms, so imagine that you want to estimate a BS norm. So you will end up with BS plus 2 norms of these two terms, but which has been controlled here, okay? So the answer in that case, you deduce the following additional estimate for W, which is smaller again than the data. For low frequencies. So what happens for in the dense case? So is it different in diffusive case? Yes, in diffusive case, what is going to happen is that here you have something of order 2. And here the orders of operator are still the same. But if you are of order 2, this term will become negligible for high frequencies, not for low frequencies. Okay? And for these two terms, it's exactly what happened before, provided you, how can I say that? No, I'm cheating a little. Right. In that case, a bit more complicated. You have to, what did I do? Should work in principle. So this one is definitely negligible compared to the other ones. No, okay, I see what happens. Well, okay, you can still get something, but you have to do what you have to do. That you have to do. You have to do to work more. Okay, you have also to write. I will just explain what you can do, so that it works. You have to use BS plus 1 regularity for Z1. Okay, for high frequencies. And provided you do that, then you have to write the equation for Z1. Okay, you have to write again the system like a coupled system. There will be one equation for Z1, one equation for W. And in the end, if you do that for high frequencies, you will get. I'm cheating a little because then I will need 10 more minutes to do all the computation details. But what you will get indeed is a control of this term for high frequencies. Okay, so the conclusion is that in order to see the difference between these two kinds of equations, in fact, you have to do just the general inequality is not enough. You have to find some mode which corresponds to the parabolic mode in this case, or to the damp mode in the first case. Okay, I think now it's really time to start with nonlinear problems. Okay, I mean, this is not particularly difficult, but it's just that you have to do one more step, because in that way, you see, I cannot conclude because, well, yeah, what I have from here, from the beginning of the proof is not enough. In order to conclude, you have to do, you have to consider Z1 and the W at a different level of regularity for higher frequencies. Okay, so any question on that? So it is the end of the linear part. So I don't have much time for the nonlinear part, but so probably I will not take on at all parabolic problems, but at least I want to do something on that problem. For that, before that, I think it's interesting to recall some basic results for hyperbolic systems from quasi-linear first-order hyperbolic systems, because it will explain some choices that I will make for the partially dissipative situation. So let's call it Yeah. Yeah. It's much more difficult. I mean, it depends what you call nonlinear. If nonlinear is that you have a linear part plus nonlinear, then still you can put the nonlinear part as in the right hand side, and if you have good structure hypothesis, then you can get a global result for small data. But if you think as something like interesting, like even dimension 1, you put the damping, I don't know, u square or u cube to with the right sign. Well, it looks to be very difficult. Even what it has been studied a little, but no, this is a complicated issue. It's not. In particular, if you think of Burger's equation, okay, in Burger's equation, if you put a cubic damping, you will see that in fact you have a global distance for small data. But if you do the same in the Euler equation, you put u cube, it's not clear at all what happens. Maybe it has been studied that maybe you have finite time blow up even for small data, I don't know. But clearly these methods do not work at all. Okay, so let's call it nonlinear, partially nonlinear, partially dissipative systems. Okay, so I start with the first paragraph. I am not even sure that I will do more today. I will recall some results about a pure hyperbolic case. So, what kind of system I want to study? I will call them H for hyperbolic. So I want to look at this system. This system can be formally deduced from the general conservation laws that I gave the first course. They write like this. So you have some matrix A0 of U, DTU. So maybe do not, I'm going to write DTV. I will explain why. Okay. And then you have sum from 1 to D of AJ U DTV equal, well, you may have, here you may have some nonlinear terms or linear, you may have some first order terms. Okay. But I take 0 for simplicity, just to have shorter computations. Okay, I take 0 in order that it is faster. Okay. And so what is the relationship between U and V? So remember that all the matrices are defined on, so they are defined on some phase space, which is a subset, open subset of Rn, and values in Rn. I will add some assumptions after, okay? Definitely you did that, oh sorry, it's not DT. Okay. And I assume that V, in fact, I look at some perturbation of some reference constant state, U bar. Why do I do this? Because very often, in fact, you are not interested, if you think of Euler equation, in general, the reference state is not density 0, it's rather density which is positive. Well, it depends. You may also try to solve compressible Euler equations with a vacuum in the far field, but well, it's a different story. Okay, so I prefer to write it in that way. And my question is local well-posedness in Sobolev spaces. Or in any spaces, by the way, but we will see very easily, very fast, that Sobolev spaces are the most natural ones. So how can you prove this? So clearly I need some assumption, otherwise it can be ill-posed even. So the assumption that I'm going to do is that the system is what we call symmetrizable. Symmetrizable, which means that there exists another matrix. So from the phase space to Rn to no, it's a matrix. Sorry, to M and R. Such that S is a symmetric definitely positive. And I also need that all the matrices, so S0, I will denote this by S0 tilde, is a symmetric definitely positive, and all the other matrices are symmetric. Okay, real symmetric. They are all, everybody is real. So the question is how to, so I am not going really to prove existence, I will not going to be the full proof. I will concentrate on the proof of estimate, okay? Because it will explain what I will do later for this situation. So the most difficult step, almost, is to derive L2 estimate. It's not exactly the most difficult, but I mean the key step is this one, because if you understand how to do it, the rest will just be technicalities, that's all, not more. So, energy estimate, how could you do that? Okay, so you take the first equation, you multiply by S, okay, so that you have only, once it's multiplied on the left by S, you have only symmetric matrices. This is the reason why it's called, this S is called a symmetrizer. And in a difficult issue that occupied many people in the 70s and 80s is to construct symmetrizers for different classes of systems. For example, for Euler equations, if as I wrote it 2 days ago, it's not symmetric. If you want to do something with it, you have to symmetrize it. So you have to multiply on the left by a suitable matrix. And there are several possible choices that give different results, depending on what you want to do. Okay, so I multiply on the left by S, so that I have only symmetric matrices. And then I take the scalar product in Rn, or in L2 Rn with V. Okay? So multiply left multiplied by S, then L2 scalar product with U. Okay, so what does it give? So it gives, with the notation that I used before, with the tilde, you will have what? You will have this. Okay, so okay. You have this, your scalar product of this with this, and all the sum. In the sum, in order to understand when the symmetric assumption will come into play, it's interesting to look what happens component by component. Okay, so okay, I have my matrix AJ on U, acting on U, so this is a matrix with two indices. So it was acting on UL, and then you take the scalar product with UK. Equals 0. Okay, so what you are going to do for this one is, for these ones, what you are going to do is to put the dt outside, and then there will be a remainder terms that you can compute by using the symmetry of A0. More or less, you will end up with a U squared times the derivative of A0U. Okay? For this one, you will integrate by part. Okay, but I want, okay, so I want to compute this more precisely. So I need a name. So, let's call it JGKL. Okay, so I do integration by part. So there will be one term with the DJ acting here. So there will be this one. UL. And another term where the derivative acts on the matrix A. Okay, so maybe what is the philosophy of what I want to do? The philosophy is that I would like, so at the level of generality, there is no reason why the L2 norm should be conserved, okay? But what I would like is to have a control of L2 norm, which is quite easy to handle, so that I can iterate the process. So a good choice would be to, so for this term, this is quite clear. A good choice is to take, okay, I apply Euler inequality, I put L2 norm here, and here I have L infinity norm. Okay? But clearly I cannot do that in this term, because if I take L2 and again L2, then I will need an information that still do not have so far. I mean the H1 norm of U. Okay, but now if you assume symmetry, then this term is the same as you can swap the indices K and L. And then by changing the notation in the sum, you see that these terms exactly correspond to this one. Okay? So here comes into play the symmetry assumption. It ensures that this term is the same as this one, and consequently, well, this term is half of this one with a minus. Okay, so in the end, what you get, if you put everything together, so as I said, if you put this dt outside, you make see this term as the time derivative of this quantity. Apply to U. Okay, so here it's a scalar product. Here you have a product between a matrix and a vector. Okay, and on the right-hand side, you have something that I could denote. Maybe the notation is not perfect, but it's kind of divergence, acting divergence with respect not only to space variable, but because of that one to the time variable. So on all, this is not short notation, saying that here you will have derivatives of all matrices. Okay, so ATD of U. Sorry, I put, I should go back. Sorry for that. I did a mistake here. It's not U everywhere, it's V. Excuse me. Okay. The reason why I changed the notation before, you do not, you do all the scalar product with V, sorry. So the U, you keep the U only inside the matrices. Okay. Now it's good. So you have U. So this is, once you compute this divergent operator, which amounts to put delta J everywhere, this gives you, this is still a matrix that acts on U on two vectors. Okay? Well, notation may maybe not perfect, but at least what it means that here you have derivative and here you have none. Okay, and so from that, and if you do some uniform positivity assumption, this is equivalent to the L2 norm square, and you end up with an inequality of this type, with something which is not exactly the L2 norm, but which is a kind of weighted L2 norm, which depends on A0, smaller than some constant. Sorry, again, it's V. Gradient of U. Or here you can put U on V. It's an even gradient with respect to all variables. VL square. And then you can play with Grandval lemma to get control of V. Typically, Grandval will give this kind of inequality. Exponential of C gradient of U. Okay, well, the question is clearly it's not enough to get an existence result, a well-poisonous result, because here you have only controlled the L2 norm. You have provided you have this information, which is information which involves a lot of regularity. Okay, so the classical way, so the question is how to control the term in the exponential. Okay. So the naive way of doing that is to say, okay, what I did with the L2 norm, I will try to do it with the H1 norm. So I take one derivative of the equation and I try to do the same computation. So it works in the sense that what is important to do if you take one derivative, first derivatives, is somehow to keep the structure of the system, because really the key term was this one. Okay. So you have to write the system in such a way that you keep this structure and so that the overterms are harmless. So it's doable. You can do it as many times as you want. The computations are more and more cumbersome. It's doable, but you can do it in a faster way by applying an operator that treats all derivatives at the same time up to order S. So let me do it. Well, at least explain how it works. Oh, sorry. Well, I shouldn't erase, but now it's too late. Okay, well, so higher order estimate. So before doing higher order estimate, you see from the first computation that it was important to use L2 energy argument, because if you try to do the same with LP, clearly you will not be able to take advantage of the structure of the matrices. Okay, and indeed it may proved that for almost all hyperbolic systems, there is no good LP theory. Well, there is an interesting exception, of course, which is dimension 1, but apart from that. Okay, so higher order estimate, so you defined the fractional, okay, so let me introduce fractional derivative operator. So in Fourier space, it is what? It is, okay, you take the product with this. Okay, so the interest, of course, is that the L2 norm of SZ is exactly the non-homogeneous Sobolev norm. You could do the same with homogeneous. Okay, in that case, you keep only the psi. You move the one. Okay, so what is the idea? The idea is that I'm going to apply this operator to the equation. Okay, for simplicity, I take A0 equal identity. Otherwise, I will have one more term to handle. But it could work even in this case. Okay, so let me apply this operator to the system. Okay, so for the first term, I have no problem because this acts only on space variable. But for the sum, I have to be careful because clearly I cannot do that. What I'm going to do, I'm not allowed to do that. So of course, there is an error that I can write like a commutator. So what is the error? The error is exactly the commutator between the matrix and the operator. So for the left-hand side, you can repeat what I did at the L2 level. Okay, so you know exactly what it is going to give. The first one will generate the time derivative of the square of the L2 norm of this. And here you will integrate by parts and repeat exactly what I did before. And you will end up with something that can be bounded by the gradient of the matrix times the square of the SSV L2 norm. And this is good because it may be handled as before by Grunwald lemma. So the question is this term. So for this term, it suffices to estimate the L2 norm, okay? Because if you take scalar product with V in L2, you will apply Cauchy-Schwarz inequality. And then to estimate it, you can use something which is well known, but nevertheless very interesting and useful. It's Cato-Ponce commutator estimate, which says that whenever S is positive, or even 0, but for 0 it's not interesting. It's obvious, I mean. You have, sorry. Oh, I can't, no, okay, I will leave the matrix. Okay, so I want to bound the L2 norm of this. So the answer is that whenever S is positive, it may be bounded by the following two terms. So the first one is a gradient. In fact, the problem with this term is that it seems that you lose one derivative. But thanks to the commutator, we'll be able to put the derivative on it. Okay, it's exactly the terms that I had by integration by parts before. Okay, and so for this one, you will have V, HS. And you have a second term. The second term is a L infinity norm of this one. Times the gradient of HS minus 1 of this. So, okay, this one is by the chain rule, you may bound this one by the gradient of V. And for this one, it's a bit more complicated, but it's possible to bound this by the HS norm of U times some constant that only depends on the NFT norm of U. Okay. So you end up with this kind of inequality again. So the result is the following one. So you know that it's equivalent to the HS norm. This one and C gradient of V, or for U equivalently, times VHS square. Okay, I mean, the only difficult part here is Cato-Ponce commutator estimate that have been proved for long. So once you have this, it's very easy. So the question is how big S should be if you want to get some control on HS norm, because you see that here you can use Grunwald lemma as before, but you still have the same problem. There will be the integral from 0 of t to this term that will appear. So in order to conclude, you need to have a S which is high enough to control this term. And high enough means greater than 1 plus d over 2, because in this case, indeed, you have a control of this by the norm H1 HS. Okay, so if you take S like this, then Ujjwal will imply this kind of inequality. You may notice that at least formally I can simplify by VHS once. Well, it's formal, but you can make it rigorous. And then you have this inequality, which is a Riccati type. Well, with equality, it will be a Riccati equation. It's a Riccati inequality. I never know if there are 2C and 1T or the opposite. 2C? Okay. And from this, you get a control of V on some time interval, which is some constant, which may be computed like this one, another constant, divided by the HS norm. Okay, very often, in fact, in most of evolutionary problems that I know, where you have only local existence, the final step is this one. You end up with a Riccati equation, very often. Sometimes not a square, something a bit different, but always in the same spirit. But there is so the first, I mean, historically, the first method of doing this was taking integer derivatives enough times. It's very cumbersome computations. You have to be very smart to handle all the huge sum that you get and to use plenty of times Euler and Gallardo-Nirenberg inequalities to conclude. Then this method is slightly more modern because it's based on this Cato-Ponce estimate that has been proved around 85, I would say. And there is still a more modern way of doing it that I want to present because it's the one that we use for dissipative systems, which is based on Littlewood-Paley decomposition. The spirit is the same, except that instead of applying this operator lambda S to the equation, I will apply the Littlewood-Paley operator. So with Littlewood-Paley operator, delta J. In fact, in this context, it would be, I will do it with homogeneous ones, which are not exactly adapted to this context. But anyway, I don't want to define a new notation, so I will keep this one. Okay, so I do the same. No, I will not use J because J is already for derivative, so I need the letter Q. Okay, so I apply delta Q to the equation. It's exactly, the first step is exactly the same. Only the name of the operator has changed. Okay, so AGU, DJ, delta K V. And again, I have a commutator term, which is the commutator between AJU. Actually, it is a generic proof that you can do with any operator. The only question that has been solved is how to bound the commutator. Sorry, dot. Okay, so the operator that I defined before. Here, I have only dots. So, again, I am going to use a commutator estimate, which looks very similar to the one you will see. Formally, there are very few differences. And again, you are interested by the L2 norm. So you will have to pay for some constant. Here there will be over two constants that I will indicate after. So what is the difference? So the first term here is the same, almost the same. So again, I have this one. So if I use a Littlewood-Paley operator, I have the choice. I mean, I have more degree of freedoms. I have different kind of Bezos spaces that I can use. I could use again Sobel spaces, but it wouldn't be interesting because I already have the result. I chose the L2 norm, so it restricts the class to spaces of type BS2 something, and the last index to be in accordance with what I did before, and also because it's the one that gives the best result for this. I will keep the Bezos norm BS21. Okay, and with this choice, in fact, you have to put this, okay, so that if you multiply by 2 to the GS and sum, you will get well, the usual Bezos norm. And you have a second term, which is what? The second term is probably it's the same, it's gradient V of L2 and the Bezos norm of this BS minus 1. I have to explain what are these constants Cj. They are such that if you take the sum, you find 1. And they are non-negative, of course. I could have wrote, in fact, in another way, equivalently, you can say that if you take the sum of the left-hand side times 2 to the JS, then you are bounded by all this. Okay? So I am not going to prove this. It's been proved by different, you can find this in different places, different monographs and papers which use Littlewood-Paley operator. I have no idea who first proved this. Maybe Jean-Yves Chemin, I'm not sure. Okay, so once you do this, what you do is what? Okay, you compute the L2, some collision of notation. It's not J, it's Q. J is for the derivative. They are not, and here also it's Q. Okay, so once you get this, you take the L2 norm, you bound the right-hand side in this way. you multiply by 2 to the QS, and you sum, and you end up with always the same kind of inequality. You end up, again, with a Riccati type equation. Except that there is some technical point, is that the index that you want in the end, okay, you want a relatively high index, which is greater than 1 plus d/2. And in this range, the Bezier spaces are not longer well defined in the sense that they are no longer complete. So, in fact, the relevant space that it's better to use is a non-homogeneous version of it, which is just the intersection of L2, so that you have a control of low frequencies. And you know how to estimate L2 anyway, and times this one. Okay, and so you end up with this inequality with no dot. Okay, and I recall last time I proved that L infinity, or BD/2 was embedded in L infinity. So if you want to control on the gradient, you have to take one more derivative. Okay, the Lipschitz norm is controlled by this one. Consequently, you end up with local well-posedness. So the result has been first proved by Yves Tinier in 1999. You have local well-posedness in this space. Of course, you also have a well-posedness in a BS21 with S greater than this, but this seems to be the critical level of regularity. Okay, and the advantage of this Bezier spaces is that you can achieve critical regularity. I mean, you can achieve the critical embedding that you are not able to achieve for submodel spaces. Okay, so since I don't have so much time, I'm not sure what I'm going to do, rather than starting partially dissipative systems, is to, I don't know if it's useful or not, but as there are, some of you are master or PhD students, you are maybe not so used to proving existence theorem. Maybe it's informative, it's interesting that I recall from this, because all these are just formal estimates that you can perform on smooth solutions. But the question is now, how can you, whatever the method is, how can you really construct such solutions? So there are plenty of ways of doing it, which are more or less based on fixed point theorem. But you have to know that for hyperbolic systems, you are never able to use the Picard fixed point theorem. I mean, the one which is the contracting mapping argument. This one cannot be used for the reason that you are not able to prove that you have a Cauchy sequence in the space when you want to prove existence. Okay, I will explain very shortly why. And of course, the same will appear if you add some partially dissipative or diffusive term. So, standard scheme of standard proof of existence. In fact, rather, there certainly there is a way of taking advantage of abstract fixed point theorems by using, I don't know, kind of Schroeder-Tikhonov or whatever. But in fact, it turns out that very often it's easier to do it just by hand, okay, by repeating the arguments that lead to the proof of general abstract results. So the first step is you construct a sequence of approximate solutions. So a sequence, let's call it VP. I think that index P has not been used so far. Of approx solutions, and so that it's in order that it's easier of linear systems. So this is step one. So typically what you can do, there are other possible choices, of course, but what you can do, while you start the first term, D0 will be just the initial data. And then to go from VP to VP1, you solve the following linear system. Okay, I take A0 equal identity for simplicity. Okay, so what you are going to do is that you are going to put the previous solutions in all the matrices so that you have only, okay, so the notation is, as you can guess. Okay, so what I denoted by UP is U bar plus VP. So I am cheating a little because, okay, and you have to prescribe the initial data. So if you want to have a, well, it depends. Here you have some freedom. Either you put really the initial data, or if you prefer to work only with smooth solutions, you can decide at each step to smooth out the data also. Okay, so as you want, depends on exactly on what you want to do. So, well, there is a kind of cheating in the sense that maybe it's not so obvious to solve this problem. So maybe beforehand, you have to check that indeed there is a good theory for this kind of systems. But this kind of system is linear hyperbolic, something which is well known. So if you take it for granted, then you have your first step. So what you can do on this solution, so this solution is going to be global because it's a linear problem. So the difficulty is to get uniform bound. You have to prove, okay, well, right? Step 1 and 2 are, in general, they are done together, but you have to prove uniform bound in, let's say, C0 of, depends on your space. Okay, X may be either Sobolev space or Bezos space. It depends on what you want to do, or on any space in which you can prove estimate. Okay. With, so what is difficult? It has to be independent of P. You have to check that it doesn't shrink to 0 when P tends to infinity, okay? And so for that, you will use, in this step, you will use exactly what I did before, okay? So this estimate we are based on, finally, we end up with a Riccati type equation. And you see that here the situation is rather easy because the time on which you can do that is just the inverse of the size of the initial data, okay? So if you take a fixed initial data, it will be easy to have a fixed time. So the first step now is to prove the convergence. So this step 2, it's called a high norm estimate. So now we need to prove convergence to a solution. To a solution of the hyperbolic system. And here something bad appears. So in general, when you prove convergence of the solution, it's based on some contracting argument. So the most natural one is to try to prove that you have a Cauchy sequence. But now if you compare two terms of this sequence, okay, two consecutive terms, for example, so you will have, okay, the usual sum, that involves a difference, but then there will be something bad. The something bad is this one. Something bad is that here you have dj, delta j of typically of Vp, for example. Okay, so why is it bad? Is it bad because this is only if you start with regularity S. For example, if you are in a Sobolev space, here you are only in H S minus 1, so you lose one derivative. Okay, so because of that, it's not possible to prove convergence directly in the solution space. You lose at least one derivative. So if you want, for this particular example, if you don't want to have complicated estimates, the easier thing to do is just to prove convergence in L2. But there are other possible choices. You could choose HS minus 1. So, but the easier one is prove convergence in L2. Okay, so it's called low norm estimate. Then you have a step 4, which is not so easy sometimes. I will not give details because I have to stop. So after step 3, okay, you have a limit. And step 4, you have to check that the limit is solution. So since you have a high regularity, it's not too difficult. And sometimes more difficult belongs to this. Why is it more difficult? Because, well, what you are going to use, mostly you are going to use functional analysis type arguments. It will be easy to have L infinity. To get continuity, it's a bit more difficult. And then you have, of course, you have to prove uniqueness and stability with respect to data, but it is more or less the same as step 3. No, uniqueness and stability with respect to data. It's like step 3. Okay, I just want to point out that the stability result with respect to data that you are going to have is at the L2 level. Okay, you start with HS, but you just have stability L2. You can interpolate between your different estimates, and you will have stability for any index S prime smaller than S. To get really stability up to index S is doable, but much more difficult. Okay, let's stop here. Thanks. The coefficients?
Yeah, the matrices.
Yeah.
Time dependent.
Time dependency. Well, honestly, I don't know exactly what is the state of the art, the time dependent case. Certainly, it would be easier to do that. The worst case would be space dependent, because then, yeah, you cannot use the Fourier analysis, use the Fourier transform, and so on. Time dependency, I cannot say what happens. You probably know better than me. Mm-hmm. Okay. This I don't know.